Episode 87, titled Drift Types, Data Drift versus Concept Drift, and Expected Warning Signs, we focus on a truth that is easy to forget when a model is new and performing well. The environment will change, and models age even when no one touches their code. In cybersecurity and other operational domains, the data generating process is not static because people adapt, attackers evolve, customer behavior shifts, and systems get upgraded. That means a model that was accurate at launch can become progressively less reliable, not because the model broke, but because the world moved underneath it. Drift is the name we give to that movement, and treating drift as inevitable is healthier than treating it as an anomaly. The point of this episode is to give you a clean mental map of drift types and the warning signs that tell you when maintenance is needed. If you can classify the drift you are seeing, you can choose a response that is measured and defensible rather than reactive. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Data drift refers to changes in the distribution of input features over time, meaning the values you feed the model start to look different from what it saw during training. This can happen because user populations change, sensors are recalibrated, logging formats shift, new product features roll out, or adversaries deliberately change their behavior to evade detection. Data drift is often visible even before you look at labels because you can observe that means, ranges, frequencies, or correlations among features have shifted. In practice, data drift is the most common form of change you will notice first because it does not require waiting for outcomes to be known. It is also the drift type you can monitor most continuously because it is available at inference time for every prediction. The key is that data drift describes the inputs themselves, not whether the model's meaning remains correct. Concept drift is different because it describes a change in the relationship between features and the target, meaning the same inputs no longer imply the same outcomes. In other words, the mapping the model learned becomes outdated, even if the feature distributions appear stable. Concept drift can occur when policies change, when attackers alter tactics in ways that make old signals less predictive, or when the operational definition of the target shifts. For example, what counts as fraud or incident can change due to new rules, new thresholds, or different labeling practices, and the model's learned associations can become misaligned. Concept drift is often harder to detect quickly because it requires feedback in the form of true outcomes, and outcomes may arrive with delay. When concept drift occurs, retraining is often necessary, but only after you confirm that the target relationship truly changed rather than the model simply encountering random variation. Covariate shift is a useful special case to recognize because it describes a situation where inputs move while the underlying concept stays stable. Under covariate shift, the feature distribution changes, but the conditional relationship between features and the target remains essentially the same, meaning the meaning of the signals has not changed. This matters because the response to covariate shift can differ from the response to concept drift, especially if your model is robust and the new input distribution still falls within a reasonable operating range. Sometimes you can handle covariate shift with monitoring and possibly recalibration or mild updates, rather than full model replacement, depending on how severe the shift is. The exam angle is that covariate shift is not just vocabulary. It is a way to separate changes in what you observe from changes in what those observations imply. If you can identify covariate shift, you can avoid assuming that every input change demands a major redesign. Concept drift often reveals itself through rising error rates, even when inputs look familiar, which is why performance monitoring remains essential. You might see that the distributions of key features appear stable and the prediction score distribution looks similar, yet your realized errors increase, such as more false positives, more false negatives, or degraded calibration. That pattern suggests the world's meaning has changed, not merely its surface appearance, because the model is making the same kinds of predictions, but they are no longer correct. This can happen when adversaries learn to mimic benign patterns, when customer behavior changes due to external events, or when the labeling process changes in subtle ways. The important point is that concept drift is not always accompanied by dramatic shifts in inputs, because the change can be in the underlying mechanism that connects inputs to outcomes. If you only monitor inputs, you can miss concept drift until it causes visible harm. A disciplined monitoring approach includes 3 perspectives: key feature distributions, prediction distributions, and performance metrics based on ground truth when available. Monitoring features helps you catch data drift early, especially shifts in ranges, missingness, or category frequencies that indicate upstream changes. Monitoring prediction distributions helps you detect when the model's outputs shift, such as when scores become systematically higher or lower, which can signal drift, calibration issues, or changes in the input pipeline. Monitoring performance metrics closes the loop by telling you whether drift is affecting correctness, which is the ultimate question, but it depends on outcome feedback. In practice, you treat these as complementary because feature drift can occur without immediate performance impact, and performance can degrade even when features appear stable. The value comes from watching all 3 and looking for consistent patterns rather than betting on a single indicator. Segment monitoring is critical because drift often appears in subgroups first rather than across the entire population. A global metric can look stable while a specific region, customer segment, geography, device type, or traffic source is experiencing significant change. In cybersecurity, an adversary may target a particular subset of assets, and drift in that subset can be masked by the volume of normal traffic elsewhere. Segment monitoring helps you detect these early signals by breaking down feature distributions, prediction rates, and error metrics by meaningful slices. The trick is to choose segments that reflect how the system is used and where risk concentrates, rather than slicing at random. When you see drift in a subgroup, it often provides a clue about the cause, such as a new software version, a new partner integration, or a localized behavior shift. This is one of the most practical ways to move from detection to diagnosis. Alert thresholds for drift monitoring should be aligned to business tolerance and operational capacity because alerts are only useful if you can respond to them. If you set thresholds too tight, you will generate constant alarms and teams will start ignoring them, which is an operational failure rather than a technical one. If you set thresholds too loose, you will miss early warning signs, and drift will be discovered only after impact becomes obvious and costly. The right thresholds depend on how sensitive the application is to model error and how quickly the organization can investigate and act. In some contexts, a small degradation is acceptable, while in others, even a slight increase in misses is unacceptable and must be flagged quickly. Setting thresholds is therefore a governance decision that translates technical signals into actionable triggers. Planning retraining, triggers, and validation steps before redeploying updates is what turns drift management into an engineered process rather than an emergency response. Retraining triggers might include sustained performance degradation, persistent feature distribution shifts beyond a defined tolerance, or new data availability that reflects changed conditions. Validation before redeployment is essential because retraining on new data can fix drift but also introduce regressions, especially if the new data is biased or incomplete. The idea is to treat model updates like controlled releases, where you evaluate the candidate model under the same disciplined procedure used originally and confirm it meets performance and stability expectations. In security and risk settings, you also care about how changes affect alert volume and operational workload, not just aggregate metrics. A retraining plan that lacks validation is just swapping one unknown for another. A champion-challenger approach provides a safe mechanism to compare models under drift without forcing an all-or-nothing switch. The champion is the current production model, and the challenger is a candidate model trained on newer data or with updated features. You run them in parallel, compare predictions and outcomes, and decide whether the challenger truly improves performance and stability before promoting it. This approach reduces risk because you can observe how the challenger behaves under real traffic conditions without immediately relying on it for critical decisions. It also helps you understand whether drift is affecting all models similarly or whether a specific update addresses the change. The concept is about controlled evaluation under live conditions, not about constant churn, and it supports a measured response to drift. When used well, it becomes a routine part of lifecycle management rather than a sign that something has gone wrong. One of the hardest practical lessons is avoiding overreaction to short-term noise, because not every fluctuation is drift, and not every spike in error is a structural change. Metrics move due to randomness, seasonal effects, data collection delays, and labeling variability, and reacting to every wiggle can lead to thrashing, wasted compute, and unstable operations. Confirming sustained change means looking for persistence over an appropriate window, consistency across multiple indicators, and a plausible explanation tied to known events like releases or policy shifts. This is where segment monitoring and prediction distribution monitoring help, because they can show whether the change is broad and durable or narrow and transient. A disciplined approach treats drift detection as hypothesis generation, followed by confirmation, not as an automatic trigger to rebuild. The exam cares about this because it is the difference between mature maintenance and panic-driven modeling. Communicating drift as ongoing maintenance rather than a failure event is important because it shapes how organizations allocate resources and interpret model behavior. Drift is not an indictment of the team that built the model. It is a property of deploying models into living systems where behavior changes. When drift is framed as inevitable, teams are more likely to invest in monitoring, feedback loops, and safe update mechanisms rather than treating every issue as a crisis. This communication also helps stakeholders understand that model performance is not a one-time achievement, but a managed service that requires periodic attention. In regulated or high-stakes environments, this framing supports governance by making monitoring and retraining part of expected operations. The healthier narrative is that drift management is what keeps models trustworthy over time. The anchor memory for episode 87 is that inputs drift first, meaning drifts next, monitor both. Inputs drift first because feature distributions can shift immediately when pipelines change or populations change, and you can often observe that shift before labels arrive. Meaning drifts next because the relationship between inputs and outcomes can change over time, sometimes gradually and sometimes suddenly, and you detect it through sustained performance changes. Monitoring both matters because watching only inputs can miss concept drift, and watching only outcomes can delay detection until harm is visible. This anchor also reinforces that drift is multidimensional, appearing in subgroups, in score distributions, and in calibration, not just in a single metric. When you keep this mental model, you build monitoring that is layered and resilient rather than brittle and reactive. To conclude episode 87, titled Drift Types, Data Drift versus Concept Drift, and Expected Warning Signs, consider a concrete case and name the drift type along with one signal that would reveal it. Suppose your phishing detection model's input features, like email sender domain patterns and message structure indicators, look similar month to month, yet false negatives rise steadily as more malicious emails bypass detection. That pattern points to concept drift, and one strong signal is a sustained increase in error rate or missed detections, even though feature distributions appear stable. In contrast, if a logging format change causes a key feature to shift in range or missingness while immediate error metrics are not yet available, that points to data drift, and one strong signal is a sudden distribution shift in that feature. Being able to label the drift type and tie it to a concrete signal shows you understand the difference between the world changing on the surface and the world changing in meaning. That distinction guides what you monitor and how you respond, so the model remains reliable as conditions evolve. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.